So the final talk of the session is by ArkaprabhaGhoshal. He will tell us about local identifiability of quantum states and its application.
Good evening, everyone. So first of all, I'm very much thankful for giving me this opportunity to present my talk today. So today I will going to talk about local unidentifiability of quantum states and its application. Now, this term seems to be very weird because local unidentifiability of quantum states is very unfamiliar to us. So what does it mean is that this is a type of state property that can only arise in multipartite quantum systems. So what do I mean by multipartite quantum system is that, so there are spatially separated labs, and each of the labs holding quantum particles. And these labs can locally manipulate these quantum particles, as well as they can use classical communication for their communication purpose. Now these multipartite quantum states share some sort of correlation that cannot be created via local manipulation as well as classical communication. Now one may ask, yes, in quantum mechanics many things happen, many things may not happen. So let's consider that these multipartite quantum states hold this particular state property, that it is locally unidentifiable. But what is the real life application of such thing? Does it have any real life application? Because we are interested in a real life application. So today I will not go in any technical details. I will try to motivate what is the real life application of such thing. So whether this correlation exists in nature or not was first proposed by us, and this is available in this archive version, and these are the authors. Okay, so let us start with the very basic concept of a banking system. So we all know, we are all aware about a banking system. Okay, so there is a bank, and two participants created a joint account in the bank. So one account holder is Alice and another account holder is Bob, and they share a common bank account, right? Okay, so we know the banking system that if I want to make a transaction, then bank will provide me an OTP. Okay, so after getting that OTP, I can transact, I can debit my money. But since there is a constraint here, because since this is a joint account, so Alice cannot actually debit or transact any money without the consent of Bob, and vice versa, right? So both of them actually expect that bank will provide them a security, right? So complicated scenario happen when, for example, Alice want to debit some money, but Bob has no consent. Okay, so in this case, in classical physics, many things can happen. Alice can apply many strategies. Okay, Alice can hack Bob's computer, and Alice can manipulate him using phone calls. So many things can happen, but this will question on the security of our banking system. So let us consider that there is a bank, and the bank provided each of the holder the information about the space, that the OTP will come from a sample space having 4 particular alphabets, A, B, C, and D. And let us consider the one-time password is ACD. Okay. Now the member of the bank, what he wants? He wants that individually any account holder cannot gain the entire information of the one-time password. Because if he gain the entire information, he can actually make a transaction without the consent of the another. So he will actually distribute or share this one-time password in such a way that the individual member cannot decode the one-time password. They has to come to a common place and decode it, and then they will decide whether they make a transaction or not, right? But this Alice and Bob, they want to cheat the bank, and they want to cheat one another, right? The only freedom I have given them, that they can use phone calls and they can locally manipulate their degrees of freedom. Okay. So in this case, what Alice and Bob wants? So Alice and Bob wants to certainly predict the one-time password using their freedom. Okay. If they fail, then they will apply a second strategy. They will at least guess what is the letters in the OTP. If they guess exactly, if they guess the letters with 100% probability, then obviously there will be a chance of guessing the proper OTP much higher than the worst case scenario. Here by worst case scenario, I mean if they guess randomly. Okay. So then there will be a question on the security of the banking system. Okay. But the bank member is very clever. So they use the help of quantum mechanics. So they use some kind of encoding strategy. So the member cleverly encodes each of the letter from the sample space in Bell states. Now these Bell states are basically two spin-half particle states, and these two spin-half particles share some fundamental quantum correlation that cannot be realized by local operation and classical communication. So these states can be practically these states exist in nature, and we can create these states in lab. Okay. So somehow they encode each individual letter in Bell states. Say for example, A is encoded in phi plus, B is encoded in phi minus, C is psi plus, and so on. Now each of these Bell states can be written as a linear superposition of Pauli Z basis. Now there is a surprising nature of these 4 orthogonal Bell states. What is the nature? The nature is the following, that if I provide one of the Bell state from this set and I distribute this set to 2 spatially separated observer or spatially separated lab, and I ask them a question that what state I have given to you, can you answer me correctly? The answer is no. They cannot certainly answer what will be the state. So this particular thing reveals a type of non-locality that cannot be realized using local operation, that means locally operating in my lab, and classical communication. So this type of non-locality doesn't appear in classical physics, in classical states or classical correlation. So the banker actually, so they actually do the encoding in such states to secure the password actually. But there has to be a tighter condition. So this is a first criteria of the security. Okay. So let us consider this particular example. So the bank provided each of the account holder the information about the sample space. The sample space contains 3 specific letters A, B, and C, and the OTP will be of 2 letters. Say for example AC. So the OTP contains specific letters from that sample space in a specific order, right? And Alice and Bob know about the encoding. Okay. They know what will be the sample space, what will be the encoding. What they do not know is that which 2 Bell states has given to me and in which order. Okay. So the bank kept that thing in secret. Now if I ask Alice and Bob individually that you have the freedom of doing a local operation and classical communication. Now can you guess the OTP certainly? The answer is no. Why? Because if I choose any 2 random Bell states from a set of 3 Bell states, the possibility is 3p2, that means 6. In 6 possible ways, I can actually make a set of 6 elements. So the dimension of the Hilbert spell will extend. So there will be a set of 6 possible elements, and these 6 elements itself becomes locally indistinguishable. So if I provide one element from this set between Alice and Bob, then they cannot certainly predict what is the element. So this gives rise to another form of non-locality that is much more general than local indistinguishability. That is known as locally unmarkability. So unmarkability means that two things are possible in unmarkable set, in unmarkable set of states. That means if I choose my encoding from a set of unmarkable set, then either Alice and Bob cannot reveal the letters as well as the order, or other thing happen. They may reveal the letters, but they may not reveal the order. Okay. So This seems to be a secure protocol, but it is not, because if I ask Alice and Bob that can you guess the letters from this OTP, can you at least guess the letters? You cannot guess the order. Okay, can you guess the letters? The answer is surprisingly yes, that they can guess the letters with 100% probability. So the banking system fails. That means why? Because the worst case probability here is increased. So initially we thought that the worst case probability is 1 by 6, but since they can certainly predict the letters, they can predict it is A and C, but they do not know the order. So in this case there will be 50-50% chance of success and failure. So this gives rise to a question that does there exist much more stronger non-local states in nature via which I can actually do some encoding and I distribute my encoded state between two account holders, and they cannot reveal the order as well as they cannot reveal the identity of the OTP. Okay. So in this case, if I increase my sample space from 3 to 4, that means A, B, C, D, and I choose 2 words for my OTP, then surprisingly the answer is no for each of the question. That means in this case the Alice and Bob cannot reveal the letters contained in that OTP and the order. So this is much more secure protocol. And if the bank member apply this particular encoding strategy, then this will be a much more secure protocol than the previous one. And furthermore, we can actually generalize from a 2-party to a 3-party, and beyond 3-party, 4-party, and so on. So for example, if there are 3 account holders and we play the same game, then actually the protocol will be much secure if we encode our alphabets in a specific GHG basis. Okay. So in this case also, every member has to collaborate and come to a common lab and then decode the message. Okay. Otherwise, they cannot decrypt or decode what is the OTP actually. So there is no problem of eavesdropping and as well as authentication problem that I have discussed earlier. So in this case, the worst case probability is much low. It is 1 by 1680. It is much low. And as we increase the number of parties, the worst case probability will gradually decreases. So this ensures that this particular if we use this particular correlation, that is locally unidentifiable quantum states, and if we use in an encoding strategy, then in real life application we can get quantum advantage that classical things cannot give us. Okay. So in summary, what I want to say that the story which I have told you is actually known as a secret sharing. This is one actually application of a secret sharing. So here OTP is actually a secret, and I fix a group of people and I distribute this secret among them, and I do not trust the individual person, but if they actually collaborate in a particular lab, they can decode the message. Okay. So this is actually equivalent problem. Now as I mentioned earlier, that locally unidentifiable quantum states has a complicated state space structure, and some kind of stronger non-locality is associated with this particular type of states. That is much stronger than local unmarkability as well as local indistinguishability, and we can utilize these particular states to actually discriminate to any kind of strings. For example, one application can be entanglement distillation. So in entanglement distillation, we often need to actually identify a string of quantum states. So we are thinking about it, but we do not know that whether we can utilize this particular state space structure in other real life application. But this is one of the thing I have mentioned. So I want to first of all I want to thank Professor Guru Prasad Kaur, Professor Shibashish Ghosh, Professor Somshubra Bandopadhyay and Dr. Manik Monik for their fruitful discussions. Thank you.